Hello, everyone. We're going to go ahead and do our exam 3 review. So we've got 8 problems in our review, and these should all give you a good idea of what's going to be on the exam and also give you a little extra practice on things that we didn't necessarily go over in class. So, all right, let's get started. Example 1, this exercise is going to use the population growth model. So this is from section 4.6. We have that some bullfrogs were introduced into a small pond. The graph shows the bullfrog population for the next few years. Assume that the population grows exponentially. A, what was the initial bullfrog population? B, find a function that models the bullfrog population t years since the bullfrogs were put into the pond. We're going to round R to 4 decimal places. C, what was the projected bullfrog population after 15 years? And D, estimate how long it takes the population to reach 86,000 and round to the nearest whole number. So, all right, we've got a graph here. We see that we've got frog population in comparison to years. And so we want to use the information from the graph to develop the equations that we need and figure out the values of R, like we have here. So we have this graph. We see that the red line, is going to start at 100, which means that's our initial population. So that's part A. Our initial population is 100, so we start with 100 frogs. And then we also have this data point here that at 2 years, there were 225 frogs. So we're going to use that piece of information for part B as well to really find that value of R. And then we use that equation for part C and D as well. So here's the graph that we're using, and we're using the point 225. And we see the initial population is 100. So, all right, we're going to go ahead and go to our notes so we can go ahead and work on this problem. All right, so for example 1, we have our population growth model, which is the exponential growth or the relative growth rate, which is n of t is equal to n naught times e to the power of rt. So n naught was that initial value, which we said from the graph was 100. Then we also had another data point from the graph saying that when t was 2, meaning at 2 years, the population was 225. So for part A, we just want to know what's the initial population, which we've already said it a couple times now, but the initial population, which is n naught, is 100 bullfrogs. All right. Then part B, we want to develop an equation of this situation that's going on here. So if we want to develop the situation, we would say n of t is equal to n naught, which we said was 100, and then e to the power of, well, r and t. If we want to develop an equation, we're saying that we want to know at what specific time, what's the population going to be? That is typically going to be the problems that we want to answer. So that means that n of t and t do not have to be defined because typically we would say, oh, my population is this, find the time, or oh, the time is this, find the population. So in that case, that really the last thing we need is R. So for part B, we need to solve for R. And the only way to do that is to use the information that we were given, which was that extra data point. So we're going to use t equals 2 and n of t equal to 225 to solve for R. So this means that n of t is 225 is equal to n naught, which was 100, times e to the power of r times t, which we said was 2. So we have 225 is equal to 100 times e to the power of r times 2. So we can go ahead and simplify. We want to solve for the exponential function, so we want to get rid of the coefficient. So we're going to get rid of the 100 by dividing on each side by 100. Cancels on the right-hand side there. This will give us 2.25 is equal to e to the power of 2r. So now that we're at this point, we've isolated the exponential function. And once we've done that, we can get rid of e by taking the natural log of both sides. So we'll move that over a little bit. So here we go. So we take the natural log of both sides. The natural log and e cancel out. And the 2r comes to the front. So in this case, now we're going to have 2r is equal to the natural log of 2.25. And we want to solve for r. So to get rid of that 2, we're going to divide by 2 on each side. This leaves us that r is equal to the natural log of 2.25 divided by 2, which we can go ahead and put in our calculators. We want to round this to 4 decimal places. And if we do, you should end up getting 0.4055. And that's r. Now remember, for part B, we just want to develop an equation which required that we find r. So now that we've found r, we have to write the equation. So we're not quite done. The last part is just writing out the equation, which will be n of t is equal to 100 times e to the power of 0.4055 t. And that is our answer for part B, just like this was our answer for part A. So part B is just developing the equation for the given situation with the bullfrog problem. So part C was that we want to know how many bullfrogs are going to be here in 15 years, or how many bullfrogs are going to be in our population in 15 years. So we can use the equation that we have from part B to plug in 15 for t. So we're saying that t is 15 years, which means that n of t is really n of 15. This is equal to 100 times e to the power of 0.4055 times 15, which we plug this in our calculators. We want to round to the nearest whole number because these are frogs. So you do not have half of a frog. You do not have 0.1 of a frog. We round to the nearest whole number. So in this case, rounding to the nearest whole number, we would get that in 15 years, we'd have about 43,812 frogs, or specifically bullfrogs. So part C at this point is just plugging in a number for the amount of time that we had. Then part D, we want to know how long will it take us to get to 86,000 frogs. So for part D, now we have a specific amount of frogs or for our population, and we need to find the time. So we can go ahead and plug this in. We're saying that n of some time is going to be 86,000, which means our equation will be 86,000 is equal to 100 times e to the power of 0.4055 t. So we want to solve for t so we can get rid of the coefficient in front of the exponential function, because we want to solve for the exponential part of this. So we want to get rid of anything that's attached to it, like the 100. The 100 cancels on that side. And then we get 860 is equal to e to the power of 0.4055 t. And so we've isolated our exponential function, which means that we can now take the natural log of both sides. So we'll have the natural log of both sides there. That cancels out the natural log and the e. And you bring the exponent to the front. So this will give us 0.4055 t is equal to the natural log of 860. Now I want to solve for t, so we're going to get rid of the coefficient, 0.4055, by dividing by that value on both sides. This means t is equal to the natural log of 860 divided by 0.4055. Plugging that into a calculator, we want to round to the nearest whole number. So if we plug this value into a calculator, you should get 16.66 around there. But we do want to round to the nearest whole number. So this would be about 17 years. And there we have it. So this problem is quite a few parts. There's 4 parts to this problem, but each problem is almost a little bit like leading you through what you want to have. So parts A and C are pretty straightforward. Part B is definitely tougher. You have to find the value of R to figure out the equation. And then part D is a little tougher as well, just because you need to find the amount of time it would take to get to a specific population. We see it kind of leads us through each part a little bit. So you're not alone in trying to find the final answer. All right, so that wraps up question 1. So let's go ahead and go back on over to our review slides. All right, that was example 1. So moving on to example 2, we want to solve the logarithmic equation for x, where we have log base 3 of x plus 5 minus log base 3 of x minus 5 is equal to 2. So let's go ahead and do this in our notes. All right, so for problem 2, we do want to solve for x, but also at the same time, we are going to use the laws of logarithms. So we're going to combine section 4.4 and 4.5 together because we still want to solve for x, but we have to use those laws of logarithms from our last section, 4.4. So first thing we want to do, combine our logarithms. If we want to solve for x, we'll need the logarithm to be in one single term so that we can take a logarithm of both sides, write it in its exponential form, any of those solution kind of solving ways that we can solve for x. So we need it to be in one logarithmic term, which means that we have to use the laws of logarithms. And in this case, we have one logarithm minus another logarithm, which means that this is going to be the second law of logarithms. So we can go ahead and write that out. This is the second law of logarithms. If you don't quite remember that second law of logarithms, I highly recommend having that written down or have a note card on your exam or anything like that. Definitely have that handy for these types of problems. So our second law of logarithms says that if we have subtraction between logarithms, we can instead write that as a logarithm of a quotient. So dividing the first term in the first logarithm by the second in the second logarithm. So essentially this is going to turn our logarithm into log base 3 of x plus 5 divided by x minus 5 is equal to 2. Now, at this point, we have one single logarithmic term, and it's set equal to a number. So we can definitely try to solve for our logarithm here. The best and probably easiest way to solve for this logarithm is actually not even solving. It's just rewriting it in its exponential form. So remember that a logarithm, we say logarithm of base a of y is equal to x. We can always rewrite this as a to the power of x is equal to y. So you can always rewrite in those forms if you want one or the other. So in this case, we want the exponential form. We don't want a logarithm anymore. So we're going to rewrite everything. So we see that in this case, 3 is a, the base. 2 is x, the exponent. And y is our rational function here, x plus 5 over x minus 5. So turning our logarithm into an exponential function, we'll have a, which is 3, to the power of x, which I said was 2, is equal to y, which is x plus 5 divided by x minus 5. So here we go. We got rid of the logarithms. We just have x's, so now it's much easier for us to solve. So our first step is we're going to do 3 squared. 3 squared is 9. And I'm also going to switch the sides as well. So we're going to have x plus 5 over x minus 5 is equal to 9. Then if we want to get rid of the fraction, we can multiply each side by the denominator. So we can multiply each side by an x minus 5. And it will cancel on the right-hand side. And it will now leave us with x plus 5 is equal to 9 times x minus 5. And we're just solving for x, so we can simplify this. We can distribute that 9, and we'll have x plus 5 is equal to 9x minus 45. Once again, we want to solve for x, so we can go ahead, bring all of our x terms to one side, all of our non-x terms to one side. So we can subtract 9x from both sides. And we can also subtract 5 from both sides. And this will give us x minus 9x is negative 8x is equal to negative 45 minus 5 is negative 50. Once again, solving for x, we're going to divide each side by negative 8. And finally, we get x is equal to 50 over 8, which is also 6.25. So in this case, for problem number 2, we wanted to solve for x. We weren't given any specific like rounding instructions, and it was just 6.25, so we could just write 6.25 in this case. But this is how we would solve a problem like this. Now, I want to warn you of one thing. It's really tempting to look at this problem and immediately want to use, wrong thing. And immediately want to use the difference of squares on x plus 5 and x minus 5. But you have to remember that that minus indicates the second law of logarithms, not the first. The first law of logarithms would be a plus, and that means that you can multiply what's inside those parentheses. But it's not plus, it's minus, which means it's the second law of logarithms, and you have to write it as a quotient instead of multiplying them together. So while it is really tempting to see that and think, oh, I must have to use the difference of squares, that is not the case. So just keep that in mind for something like problem number 2. All right, let's go ahead and go on back over to our review slides. All right, that was problem 2. Now we have problem 3. We want to graph the function not by plotting points, but by starting from the graph of y equals e to the power of x in the figure below. So we have the figure given to us. And now we're going to regraph y equals 2 minus e to the power of x. So in your homework and on the review assignments, you've probably been aware already that you mostly just pick these for multiple choice. So you can expect the same thing on the test, but we will regraph it ourselves. And then at the end, we'll want to state the asymptote, the domain, and the range. So, all right, let's go on over to our notes to work this problem out. All right, so for problem 3 here, we have the graph of y equals e to the power of x already provided, and then we want to regraph y equals 2 minus e to the power of x. We want to state the domain, the range, and the asymptote that is going to, come away from this problem. Draw that one in. All right, so first thing that we want to do is mostly we just want to identify what types of transformations are happening to our graph of y equals e to the power of x. We see we have 2 minus e to the power of x. So one of the first things that we can notice is that we have a minus sign. The minus sign is going to indicate a reflection because we know that reflections come from adding negative signs either directly to x or to the entire function. So if we have negative e to the power of x versus e to the power of x, that's going to be a reflection across the x-axis. So we have a reflection across x-axis. Then we also have this 2 out front here. And the 2 out front is going to indicate to us that we have a shift. So since the 2 is being added or subtracted in this case, it's really being added to negative e to the power of x. If we rearrange this, it would say negative e to the power of x plus 2. So really what we have here is that we have a shift. We are adding, so it is going to be either up or to the left in this case, which we see it is also outside the function of e to the power of x, which means it is a vertical shift up. So we are going to have a vertical shift. I didn't realize I was hitting the top of the page there. So this is a vertical shift up by 2. So that means that we can reflect e to the power of x and then bring it up 2. So if we say that this function right here is e to the power of x, if that's e to the power of x, then the reflection across the x-axis would end up looking like this. Something like that. So that's a reflection. That's negative e to the power of x right there. Then we reflected it already. There we go. So we reflected it. This is e to the power of x. And then we have the vertical shift up by 2. So our vertical shift up by 2 means that we're going to grab that blue graph and bring it up 2 spaces. So an idea as well is that we can kind of take that one point that we have at 0, -1 and bring that up 2 spots. So we can go like that and bring it up 2 spots. And what this ends up looking like is that this is going to be our intercept. And then we're still going to have this graph coming down like in this way, in this direction. And then we come up this direction here, like that. So we shifted it up once it was already reflected. So this means that this is the graph of 2 minus e to the power of x, that green graph there. So that is what it should look like. Typically, if you have a problem like this, you always want to maybe try to do the reflections first and then any kind of shifting. So in this case, we had that reflection across the x-axis, which flipped it across the x-axis, and then that vertical shift was up, so we moved it up. You can always rewrite an equation to help you. If having the equation as y equals negative e to the power of x plus 2 helps you more, then you can always rewrite it in that way as well. So we saw the vertical shift up by 2 and then reflect across the x-axis. So now we want to state what the domain, the range, and the horizontal asymptote is going to be. So first things first, identifying the horizontal asymptote is probably going to help us quite a bit. So with the original graph of e to the power of x, the horizontal asymptote was y equals 0. So in here, there we go, horizontal asymptote is y equals 0. So when we reflected it, that horizontal asymptote didn't change, but then we moved everything up 2, which means that we also moved the horizontal asymptote up 2, which tells us the horizontal asymptote is right here at y equals 2. So we moved it up. So that horizontal asymptote should lie at the same value as the value that you shifted by. So our horizontal asymptote is y equals 2. Our domain for an exponential function is all real numbers, even though it kind of looks like it kind of curves off pretty sharply. It's going to go on forever in that case. So our domain is negative infinity to infinity. And our range here is going to be the lowest value to the highest value, which in this case, our graph is pointing downward, which tells us that our lowest value is inevitably going to have to be negative infinity because it's going kind of downwards there. So it's going to decrease forever, which means that we're going to start from negative infinity. And we see that the highest value when we come up from our graph is it's going to stop at that horizontal asymptote. We're never going to cross that horizontal asymptote at y equals 2. We're always going to get really close. We're going to hug it, but we're not quite going to really reach it or touch it at all. So our range would be from negative infinity up to 2. And because we're never actually going to reach 2, it gets parentheses instead of any brackets, since we're not technically ever reaching y equals 2. All right, and there we have it. That's how we use our transformations for exponential functions to also find horizontal asymptote, domains, and range. So, all right, let's go ahead and go back over to our review slides. All right, so that was example 3 with using transformations. Now I have example 4. We're going to find the domain of the function f of x is equal to log base 5 of x squared minus 16. So, all right, let's go ahead and do this in our notes. All right, so for example 4, we want to find the domain of this logarithm. And we always end up with questions about domain. It is one of probably the most important topics that we go through in this class. So we want to find the domain of this function. The thing we want to remember is that domains of logarithms do not include negative results or negative values of x. So you can't take a logarithm of a negative number, which means that whatever's in those parentheses can never be negative. So we're going to write that out. We cannot take a logarithm of a negative number. Or 0 for that matter. So you cannot have a logarithm of 0, and you also cannot have a logarithm of a negative number. So really what this means is that if we want to find the domain, we want to know when whatever's in those parentheses is going to be greater than 0, positive. So we would end up taking whatever we have in those parentheses and setting it greater than 0. And one thing here is that we do have log base 5. The base does not matter. So the base doesn't matter at all. You can have log base 100 and we will do this problem the exact same way. So the base of the logarithm doesn't matter. You can never take a logarithm of a negative number or 0 for whatever base that you have. So in this case, really what this problem is that we want to know when is x squared minus 16 greater than 0? This is a polynomial inequality. So we've done polynomial inequalities in section 3.7. We saw, we factor, we find the zeros, we write the intervals, we create the table, and we find when the polynomial is greater than 0. There is another option, and I'm going to show you the option after we go through the polynomial inequality. So we're going to go through the polynomial inequality here. We're going to breeze through it. It's not a terrible polynomial. So we're going to create that table and everything. But we want to factor, so we have x squared minus 16. This is a difference of squares. So this factors into x plus 4 times x minus 4 greater than 0, which means that our zeros are going to be negative 4 and 4. So when we write out our intervals, we've got our number line from negative infinity to infinity. Got negative 4 and 4. Since we have a strict inequality here, they both cannot be included. And our intervals are everything in between. So we've got negative infinity to negative 4, negative 4 to 4, and 4 to infinity. So we are going to create the chart, create the table. So we've got sine of negative infinity to -4, -4 to 4, and 4 to infinity. And then over here we have our factors, x plus 4, x minus 4. We need a little bit more room. And then lastly, we have p of x, where this right here is p of x. X squared minus 16. So we're going to go ahead, we're going to fill in our table here. We can pick test points. So in the interval negative infinity to -4, we can say, you know, test point is -5, 0, and 5. Plugging those in, we would see that x plus 4 is negative on the first interval, and x minus 4 is also negative on that first interval, which means that our polynomial is positive on the first interval. Then when we have 0, 0 plus 4 is positive, 0 minus 4 is negative, which means that our polynomial is negative on the interval. Then with using 5, we have that x plus 4 is positive, so is x minus 4, which means that our polynomial is also positive on that interval. And that's what we wanted. We wanted to know when is p of x positive. So we see that p of x is going to be positive on both of these intervals, meaning that our answer is negative infinity to -4 and 4 to infinity. So I went through that a little bit fast, just to kind of get through that, refresh a little bit on how we did polynomial inequalities, just a reminder. So that is one option that you could use. So we'll say this is option 1. This is using polynomial inequalities. Another option that you have, option 2, is that you can kind of use a little bit of a trick. If you understand what happens when you take a square root of a number, we understand that if we take a square root of like 4, it comes out to plus and minus 2. Typically, we take the square root of x and the square root of the number, and then we put that plus or minus on the number. We could have always put it on the x and not the number, and it still technically would have worked out the same. But in this case with inequalities, it actually doesn't work out the same. So what we're going to do here is that we're going to grab the x squared minus 16 and have it greater than or equal to 0. And we can solve for x. We can add 16 to both sides. We get x squared is greater than 16. The only way to get rid of the square is to take a square root. So we take the square root of both sides. And we would get x greater than, and typically this is where we would write plus or minus 4. Instead, we're going to write plus or minus x instead. And the reason we do this is if you write x is greater than plus or minus 4, you actually don't quite get the same intervals that we're really trying to get at here. So instead, we put the plus or minus on the x, which means that we have both versions. X is greater than 4 and negative x is greater than 4. So we can separate them. So we have x is greater than 4 and negative x is greater than 4. X being greater than 4 is pretty much already done. The interval that corresponds to this is 4 to infinity. And then we have negative x is greater than 4. We can get rid of that -1 by multiplying or dividing by -1 on both sides. Then we get x is less than, because since we divided by a negative number, the sign switches. x is less than -4. And this corresponds to the interval -infinity to -4. So we have two intervals. These are both the correct answers. When you write your answer in interval notation, you would always write the lower one first, which means that our answer is -infinity to -4 and 4 to infinity. Same answer either way. You have two options of doing a problem like this. If you remember polynomial inequalities and you feel like you're good at them and this is what you would want to do, then absolutely you can use option number 1. If you would rather use option number 2, you can also use option number 2. I just warn you that it can be a little bit more confusing if you don't know kind of exactly where you're going. Because if you put that plus or minus on the 4, your answer will only have one of these intervals, and that would be half the answer is wrong or half the answer is missing in that case. So you can pick whichever option that you like better. One is obviously a little bit shorter, but we already know the other one. So it would be up to you for which one you would want. All right, that wraps up that example. Let's go ahead and go back to our review slides. All right, so that was example 4. Moving on, we have example 5. We want to use the laws of logarithms to combine the expression. So we're not solving for any x's or y's or z's in this case. We are just simplifying to combine. We have 2 times log base 7 of x plus 3 times log base 7 of y minus 4 times log base 7 of z. So we're going to go ahead and go over to our notes so we can simplify our expression using the laws of logarithms to combine them. All right, so here we are with problem 5. We want to combine. Remember, combine means take multiple logarithmic terms and turn them into one single logarithmic term. Expand is to take one logarithmic term and turn it into multiple logarithmic terms. So in this case, we have multiple logarithmic terms. We want to put them into one, which means that we are combining. So we are trying to, condense down into one logarithmic term. So if you're looking at the laws of logarithms, exactly how we kind of saw them in section 4.4, the right-hand side is the expanded version, the left-hand side is the combined version. So we want to combine. All right, so our first step here is that we have this 2 on the outside. It's affecting all of the logarithmic terms. So we're going to go ahead and we're going to distribute that 2 out first. So we're not using any laws of logarithms just yet. We are just going to distribute. So this becomes 2 log base 7 of x plus 6 log base 7 of y minus 8 log base 7 of z. All right, so we distributed the 2. Now we have coefficients in front of all of our logarithms. It is best to get rid of those coefficients first and then deal with the rest of the laws of logarithms. So since we have coefficients, this is indicating exponents on our variables instead. So we can go ahead and we can do this right away. We don't have to do this right away, but it does kind of make it a little bit easier. So we're going to use the third law of logarithms first. So the third law of logarithms, we're going to take those coefficients and turn them back into exponents on our variables. So this means that we'll have log base 7 of x squared plus log base 7 of y to the power of 6 minus log base 7 of z to the power of 8. So we turned all the coefficients into exponents. And now we have a plus and a minus sign, which is indicating the first and second law of logarithms. And you can take them in as many, steps or whatever order that you would like. I typically just kind of go from left to right. So in this case, I'm going to do the first law of logarithms first with the first 2 terms. You can do the second law of logarithms with the second 2 terms if you'd like. The order really doesn't matter once you've put those coefficients into exponents. I would say that that is usually a really good first step, and the other laws of logarithms aren't nearly as consequential after that. But getting rid of those coefficients first and turning them into exponents is usually a really good first step. But typically the order shouldn't matter. You should get the right answer in the end, whichever way that you do it. But all right, so we're going to use the first law of logarithms on those first two terms. The first law of logarithms tells us that if we are adding two logarithms, we can multiply what's inside those parentheses instead into one logarithm. So this would simplify into log base 7 of x squared times y to the power of 6. So we simplify that first two terms. We still have minus log base 7 of z to the power of 8. And so now what we have is subtraction of two logarithms, which is the second law of logarithms. So the second law of logarithms tells us that we can take what's inside the parentheses of our logarithm and divide instead, and combine into our final logarithmic term, log base 7 of x squared times y to the power of 6 divided by z to the power of 8. And that there should be our final answer. We saw we took an expression that had three separate logarithmic terms with coefficients in front. We turned them all into exponents, combined all the logarithmic terms so that we finally have one final logarithmic term, which is our answer here. So, all right, that wraps up example 5. Let's go ahead and go back to our review slides. All right, that was example 5. Moving on to example 6, we want to consider the following function. 4 to the power of 3 minus 7x is equal to 11. Part A, we're going to find the exact solution of the exponential equation in terms of logarithms. And then part B, we're going to use a calculator to find the approximation of the solution rounded to 6 decimal places. So the difference between part A and part B is that part A is the answer you get before you pick up a calculator. Part B is the answer you get when you use a calculator. So part A is the answer without a calculator. Part B is the answer with a calculator. So that's the difference between part A and part B. And our function is 4 to the power of 3 minus 7x is equal to 11. So let's go ahead and go on over to our notes to solve this problem. All right, so example 6, we have 4 to the power of 3 minus 7x is equal to 11. For part A, we want to find the exact solution, so without a calculator. Part B, we're going to find the approximate solution, so with a calculator in that case. So for part A, how we want to start this is that we see we have an exponential function, and the base is 4. So it's not necessarily 10 or e. If it were 10, we could use the common logarithm. If it were e, we could use the natural logarithm, and it would simplify very nicely. But instead we have base 4. So we have two options here. And we're going to do option 1 first. And option 1 is to take a logarithm of both sides, that logarithm being the common or the natural logarithm. So you'd want to take log or natural log of both sides. I typically like to use the common logarithm, although the natural logarithm works the exact same way. So if we use the natural logarithm, we could take the logarithm of both sides. We have log of 4 to the power of 3 minus 7x is equal to log of 11. So what happens here now is that since we have an exponent, we can use that third law of logarithms to take the 3 minus 7x out into a coefficient. So the third law of logarithms will allow us to take the expression, bring it out to the front. This is going to give us 3 minus 7x times log of 4. We got to get rid of the exponent, but the log of 4 has to stay, and the 4 has to stay. So we have log of 4, and then this is still equal to log of 11. Since we want to solve for x, we want to simplify and isolate x as much as possible. And since we have log of 4 on the same side with x, we can go ahead and divide out log of 4 on each side. This will cancel it out on the right-hand side, And this will leave us with 3 minus 7x is equal to log of 11 divided by log of 4. As a reminder, this is not the same thing as log of 11 over 4. So do not write that. We have log of 11 divided by log of 4. We want to solve for x. We want to get rid of that 3. We want to get rid of the negative 7. So our first step is that we can subtract the 3 from both sides. This will give us negative 7x is equal to log of 11 divided by log of 4 minus 3. We want to get rid of that negative 7. So we can divide each side by negative 7. This gives us x is equal to negative log of 11 divided by log of 4 minus 3 all over 7. So that is an exact solution. We never used a calculator. That is for part B. So we never once used a calculator. We never really simplified anything that we really couldn't simplify. So that's how we got to our exact solution. And that, once again, is with taking a log or a natural log of both sides. Now you do have another option. You do have option number 2. And the second option is really only going to help you if you have a calculator that can take a logarithm of any base. As I've said before, a lot of calculators can, they're not all the same, and some can and some cannot. So it really depends on the certain calculator that you specifically have. Option 1 will work all of the time, no matter what kind of calculator that you have. But if you have a calculator that can calculate a logarithm of any base, instead of taking a log or a natural log of both sides, kind of the generic way, you can take log base 4. So the same logarithm with the same base as the base of the exponent. You could even use option 2 and use the change of base formula in the end if you would like to do that as well. So you do have a couple options here. But option 2, take log base 4 of both sides. If we take log base 4 of both sides, we would have log base 4 of 4 to the power of 3 minus 7x is equal to log base 4 of 11. So still using that third law of logarithms, we can still bring the exponent out to the front to be a coefficient. But log base 4 of 4 is just equal to 1. So what we see happen is that we bring down that 3 minus 7x times log base 4 of 4, which is equal to 1. So really you just have 3 minus 7x times 1, which is 3 minus 7x. So we have 3 minus 7x is equal to log base 4 of 11. We want to solve for x. We can subtract 3 from both sides. We get negative 7x is equal to log base 4 of 11 minus 3. Get rid of that negative 7 by dividing by negative 7 on both sides. And we get x is equal to log base 4 of 11 minus 3. All divided by negative 7, or you can put the negative in the front, like I forgot to do. There we go, negatives in the front now. And that is also an exact solution. So both of these answers here, wrong one. Both of these answers here are exact solutions, and they are both correct. They are both considered correct. It's just kind of based on which one you have, which one is going to be easier to put into your own calculator. Part B is the approximate solution. You want to plug in the expressions that you have for x and actually find the value of x. if you plug these values into your calculator and solve for x, you want to round to 6 decimal places, you would get x is equal to 0.181469. And that would be your answer for part B. So part B is the decimal answer. Part A would be the exact solutions, aka something that's going to have the logarithms in them and all of that without picking up a calculator. So, all right, that was example 6. So let's go ahead and go back to our review slides to move on. All right, so that was example 6. Moving on to example 7, we have that this exercise uses the radioactive decay model. So we have radium-221 has a half-life of 30 seconds. How long will it take for 97% of a sample to decay? We're going to round to the nearest whole number. So this problem uses the radioactive decay model. We learned that in section 4.6. So that is the equation that we are going to use. Remember, this is the one that uses the half-life formula, and also it uses that radioactive decay formula as well. So, all right, let's go ahead and go on over to our notes so we can work out this problem. All right, so with our radioactive decay model, we have m of t is equal to m naught times e to the power of negative RT, where r has a specific formula. R is equal to the natural log of 2 divided by h, where h is the half-life. We said that radium-221 has a half-life of 30 seconds, and 90% or 97% of the original amount has already decayed. So we say that m of t is 97% of the original amount that's already gone. So with m of t, we said if we had, 60% left of the original, we could use 0.6 times the original to replace, m of t. But in this case, we're saying 97% has already decayed, meaning that we have 1 minus 97%, or 1 minus 0.97 times m naught. So this means we'd have 1 minus 0.97 times m naught, which simplifies to 0.03 m naught. If we think about it, if 97% of the original amount is already gone, you only have 3% left. And 3% is 0.03 in decimal. So m of t is 0.03 times the original amount, m naught. So we can plug all of this into our equations here. We've got m of t, which we said was 0.03 m naught, is equal to m naught times e to the power of negative RT. We don't know r yet, but we can use our equation for r. So we have r is equal to the natural log of 2 divided by h, which we said was 30. So we can go ahead and plug this in our calculator. The natural log of 2 divided by 30. We're going to use 8 decimal places because remember, we want to have this as accurate as possible. So we're going to have 8 decimal places. This is about 0.023104991. So we have the value of r now, so we can go ahead and we can plug that into our equation. We've got 0.03 m naught is equal to m naught times e to the power of negative 0.023104991 t. All right. So at this point, we want to solve for time. We want to know how long has it taken to have 90% or 97% of the original gone already. So we see that we have an m naught on each side. We can get rid of that m naught by dividing. Essentially, this means that we didn't necessarily even have to know the original amount. All we needed to know was how much left of it did we have. So this will leave us with 0.03 is equal to e to the power of negative 0.023104991 t. So what we can do at this point is we can take the natural log of both sides. We've got an exponential function with an e in it, So we can go ahead, take the natural log of both sides here, make a little bit more room. There we go. To solve for t. Because remember, natural log and e are going to cancel, and that exponent is going to come out to the front. So this equation here turns it to negative 0.02310491t is equal to the natural log of 0.03. Then we want to solve for t, so we're going to get rid of that big giant ugly decimal 0.02310491, and we'll divide that on each side here. Cancels on the right hand side. Finally, we get t is equal to the natural log of 0.03 divided by negative 0.02310491. We want to round this to the nearest whole number. We'll plug this into our calculators. To the nearest whole number, we get 152 cents. And that would be our answer for that example. So when it comes to radioactive decay, it's really important to look at that question because you're almost always going to have that piece of information that's saying like, oh, this much of the original is left. This much of the original has already decayed. This much of the original has not decayed. Like those kinds of statements, which is how you're going to use or replace that M of t value most of the time. And then it just becomes solving for an exponent in an exponential function, which really just kind of boils down to making sure you can take a logarithm of each side and solving for whatever variable that you have left. All right, that wraps up example 7. Let's go ahead and go back over to our review slides. All right, that was example 7. Our last example here, example 8, we're going to solve the equation for x. We're going to round our answers to 4 decimal places if needed. You'll see the statement on a lot of different problems. It may not necessarily be needed in the problem, but it will just say that to kind of get a clear image and just like a broad statement of like how many decimal places you should be using. But all right, so we're going to solve this equation for x. We have log base 2 of x plus log base 2 of x minus 3 is equal to 2. So, all right, let's go ahead and go on over to our notes to solve this problem. All right, so example 8 here, we've got log base 2 of x plus log base 2 of x minus 3 is equal to 2. We want to use laws of logarithms, all of our techniques that we have for solving for logarithms and things like that in order to solve for x. So if we want to use any techniques on how to solve for x and like get rid of a logarithm, we need to have one single logarithmic term, which means that we have to use the laws of logarithms to turn our 2 logarithms into 1. So we're going to use the first law of logarithms. So our first law of logarithms says that if you add 2 logarithms together, it means that you can multiply what you're taking the logarithms of. So this would turn into log base 2 of x times x minus 3 is equal to 2. Now we can simplify a little bit. We can distribute this x into our expression there. We can simplify it down to be log base 2 of x squared minus 3x is equal to 2. Now is another time where we want to remember how to rewrite a logarithm into an exponential function. So as a reminder, log base a of y is equal to x translates over to be a to the power of x is equal to y. So we want to identify the values here. We see that a is 2, x is also 2, and y in this case is x squared minus 3x. So we can rewrite our logarithm to be an exponential form in order to get rid of the logarithm. So we have a to the power of x, which will be 2 to the power of 2, is equal to y, which is x squared minus 3x. So in this case, we can simplify the 2 to the power of 2. It's going to be 4. 4 is equal to x squared minus 3x. And if we bring everything over to one side, this will result in a quadratic function, which we can pretty easily factor at this point. So we can go ahead, we're going to subtract 4 from both sides. And this gives us x squared minus 3x minus 4 is equal to 0. So at this point, when we use any factoring technique that we prefer, we can think of two numbers that multiply to be -4, that also add to be -3. And when you factor, you would get x minus 4 times x plus 1 is equal to 0. And remember, we want to solve for x. So we will take each one of these separately and set them equal to 0. We'll get x minus 4 is equal to 0 and x plus 1 is equal to 0. So over here, we'll get x is equal to 4 and x is equal to -1. Now at this point, well, hey, solve for x. X is 4, -1. Wasn't too bad. Definitely could have been worse. But we want to remember one thing. You cannot take a logarithm of a negative number. We got that x is -1. If we look at our functions here, if we let x be -1, that would be log base 2 of -1 plus log base 2 of -4, because it's -1 minus 3. And that is two separate logarithms of negative numbers, which we just can't have. So even though we found our final answers, -1 and 4, our logarithm actually isn't even defined for x equals -1. So in our final answer, we get x is 4 and not x equals -1. So x cannot equal -1 since we can't take a logarithm of a negative number. So with a problem like this, even though you actually can find two values of x, one of those values of x doesn't even exist in the domain of the logarithm, which means that it is not a viable value of x. So in this case, only x equals 4 is the right answer in solving for x. So, all right, that was our last example there, which finishes up our exam 3 review. So I wish you all the best of luck with exam 3. You can always email me or talk to me in office hours or anything like that if you ever have any questions about it. And I wish you all good luck.